Dear colleagues, good day. We have the second masterclass lecture. The first one was in the morning by Matteo Vajoli, and we will come back maybe to the question related to this lecture. And I would like, with my great pleasure, to give opportunity for Professor Proud to continue his very exciting cycle of lectures. Please, Bill.
Okay, so I just thank everybody again for coming along today. And today I'm going to give a presentation mainly about the use of gauges of different types, but obviously referencing high strain rate properties of material. And also, but mainly from the point of view of measuring points or lines of material behavior during high-speed loading. Many of you, if you've worked in the area of shock waves, will have come across the use of stress gauges and strain gauges and particle velocity gauges. This is, again, very much an overview. Hopefully, those of you who are less familiar with these areas will find it of interest. And I hope that you get something to take away from this. Okay, I shall now share the PowerPoint, and hopefully you can continue to hear me. So in the first lecture, first presentation, I talked about the use of waves and wave transmission being a very important factor, and that there was elastic waves and plastic waves. When we get onto the case of shock waves, we have a situation where the impact load is putting so much energy into the material, it causes a severe compression. Normally in the laboratory, we're looking about 20% compression. The limit, according to the literature, is when you push the atoms towards their thermic surfaces, and on average, that represents a compression by a factor of 2, so 50% compression. When you're in those extreme conditions, there is a generally a large stress wave called a shock wave, which is supersonic with respect to the material that is launched into the material. Basically, so much energy and force is being delivered that inertia has a huge effect. The material does not have time to move sideways away from the oncoming stress. And these shock conditions are associated with a fairly limited number of variables in the first instance. Those things are the wave speed, how fast is the wave moving through the material, the particle velocity, so how fast is the particles behind the wave going. That stress wave has direction, has energy. It puts those particles of the material in motion in the direction of the shock wave. This is called the particle velocity. I've mentioned energy, that is put in there in a very large amount. Energy, which we sometimes think of in the terms of temperature. Density of material, that's another one. And then we've got things like strain or specific volume of material. So specific volume is the volume occupied by 1 gram or 1 standard amount of material. Then we have stress in the system. So we have a fairly limited number of variables in the classic case of shockwave behavior. And we can try to measure what is happening both within and on the surface of the material. So I'm going to start by talking about the use of stress gauges, a little bit about strain gauges, and then particle velocity gauges. So stress gauges and particle velocity gauges, and sometimes strain gauges, can be used to measure the behavior within the bulk of the material. Now, here we have a block of material. This is your sample. And in plate impact, what we do is we hit it with a fast-moving impactor, generally fired out of a barrel, therefore generally circular in cross-section. It hits the target and sends a wave into it. We cut the target and we put a gauge within the target to measure the longitudinal stress. I've called that sigma Z for ease. You can also cut the sample along the direction of impact, and you can mount a thing called a lateral stress gauge. Lateral stress gauges were introduced in the late 1980s. Longitudinal stress gauges were introduced by and large in the shockwave community in the early 1980s. There was some degree of controversy over the use of the lateral stress gauge, and slightly less controversy over the use of the longitudinal stress gauge. But again, as long as we recognize that these gauges measure stress, but there are always complicating factors. You can make life very complicated, but here, again, very straightforward, first order level, we can make a measure of longitudinal and lateral stress, but we have to be careful in interpretation. We can also mount a strain gauge within the material, measuring the strain in the direction of the shock, and that has been successfully done on many occasions. If we think about the requirements of a gauge, I'm not going to read these all out, but something that varies with stress or pressure. You don't want things happening in the working range that affect the properties of the material in a way that is difficult to understand. You want it to be sensitive, of course. You want it to be not sensitive to things that you are not trying to measure. So many materials will have a pressure and temperature sensitivity with respect to, say, electrical resistance. So we look for materials which are good stress sensitivity, very low temperature sensitivity. We want them to be stable, and very importantly, you do not want these gauges or any of the gauges to be particularly sensitive to composition and manufacture, because this would mean you would have to calibrate every single gauge. And because these experiments are generally very destructive to the sample and the gauge, you cannot basically calibrate every single gauge. You'd always have to calibrate samples from the batch, and overall it will be a very messy experience, and you'd have very large error bars. So we don't want that kind of thing. And I've mentioned there are stress gauges. So piezo is a word that just means pressure. So piezo resistive. So you put a stress pulse to it, and the resistance changes with that stress or with that pressure level. MANGANIN is probably the most commonly used shock stress gauge. Piezoelectric, again, pressure electric. So it's a material that gives off charge when stress is put upon it. If we think about that in a little bit more depth, the electrical charge is released when there is a strain on the sample. So a change in strain caused by a change in stress causes charge to be released. And commonly ones there are PZT, lead, zirconium titanate, and quartz, and PVDF, polyvinylidene difluoride. It's a polymer. Probably PVDF is the most common piezoelectric gauge you will come across in literature. If you have a piezo-resistive gauge, you have to measure that resistance in some way. And so we use a fairly standard, obviously very simplified drawing here, a fairly standard pulse power supply to basically use the gauge as one of the arms of that Wheatstone bridge. And you trigger it and cause a big electrical current to go through the gauge for a short period of time, and you measure the change in resistance. It's fairly straightforward theoretically. There are technical challenges in ensuring that you can get a good time resolved signal. So you have to be careful about the components you're using. Now, the gauge itself. And we have some, here some examples of how you can put the gauge. You can put the gauge within the target. That is entirely normal. And so at the top we have a diagram there, and the gauge is the black rectangle with some leads coming off the side, and it's held in place by sheets of polymer and glue, generally epoxy. And down below we have a distance time diagram, XT diagram. So time is on the vertical axis, distance is on the x-axis, and the grey areas are that of the target, and the yellow area is where the gauge is mounted. And what we see here is, again referring back to the first lecture, is a wave coming in from the left hand side going towards the right. That's the black line here on the diagram, reaches this interface here. Some of that energy is transmitted, some of that energy is reflected. That wave goes through the material, reaches another interface between the polymer and the target material. Some of the wave is transmitted, some of the wave is reflected. So you get this oscillating wave within the yellow region, taking the stress in that yellow region ultimately up to the stress in the target. Now, from a practical point of view, you can put the gauge into it, you can glue it down, and generally the thickness of the gauge area is about 150 microns. The impedance of the mylar, which is the polymer sheet we use, and the epoxy is approximately equal. Not a huge difference there. And rule of thumb, we can discuss the rule of thumb as needed. You have to use a system called impedance matching, so crossing Hugonios is sometimes how it's used in literature, but 3 bounces, as in 3 oscillations of the wave, for the gauge to equilibrate to the stress in the target. Equilibrate in this sense means gets within 95% of the stress in the target. You can tell me there are other smaller waves afterwards and it keeps on ringing up for a significant period, but 3 bounces gets you within 95%, and that's a kind of a reasonable level to get to. So the time response is going to be 3 times the thickness divided by wave speed divided by the shock speed, and we can do some guesses here, educated guesses of the velocities we're talking about. So the distance is 150 microns. What is the wave speed, the shock speed within polymer? Well, about 2.5 millimeters per microsecond, 2.5 kilometers per second. So that's the kind of velocity we're talking about. And that means, doing that calculation, the response time is 180 nanoseconds. Okay, fantastic. We can also put the gauge on the rear of the sample. Here, we put the gauge with a backing of perspex, because the perspex is impedance matched to the polymers and to the epoxies. So now we're in a situation where the gauge package is the same thickness, but the impedance of the mylar, the epoxy, and the perspex is approximately equal. And 3 bounces for the gauge to equilibrate to the stress in the perspex, no longer the stress in the target. If we look at that XT diagram, we see the wave coming in from the left, goes, reaches that interface. Some energy is transmitted, some is reflected back into the target. So now we're in a situation where the wave goes through the epoxy, reaches where the gauge position is, there's some bounces there within the gauge, continue. So only the gauge is impedance mismatch. Now, the time response, 3 bounces, sound speed. Manganin is a metal, it's got a higher sound speed, it's about 5 millimeters per microsecond, and the gauge thickness is now 50 microns. So the response time is 30 nanoseconds. Fantastic. But here is, again, you can never get something for nothing, in the sense that we have got a higher time resolution, which is good. We've increased that time resolution by, a factor of 6 or so, factor of 7. So it's a reasonable increase in time resolution, but we're now measuring the stress in the perspex. And that means we need to apply a transmission coefficient. We need to know what is happening at that sample perspex interface. So again, we've seen this equation before. It was in the last lecture. The amount transmitted, that's in the blue background there. The amount transmitted depends upon the impedance of the perspex and the impedance of the target. You can ask me how I know in a shock environment where the stress is changing. How do I know what is the shock stress of the material? There are a number of ways of arriving at that, but what we generally do is put one embedded gauge in the system. So we do know the stress within the target, and that gives us the stress level. And we put another gauge on the rear of the target to give us more detail with respect to the time resolution. By using two gauges in the system, we can also measure the time between those two gauges, knowing the thickness of the epoxy and the sound speed in the epoxies. And you can adjust those velocities depending on the stress you're getting to. So basically, you're using two gauges to give you extra information which you can compare between those two diagnostics. So one thing, if you ever talk to me, I can become very insistent and very boring, is use as many useful diagnostics as possible, measure things with respect to time, measure stress, try to measure them independently of one another. That doesn't mean completely different gauges, it means different information extracted from those gauge traces. And here we have an example of a shock wave, a stress pulse, being measured in copper by an embedded gauge. And I suggested it was 180 nanoseconds rise time. Well, going from the bottom to the top, we see here it's a rise time of about 200 microseconds. So within the limits of a very simple calculation, we have shown that the system is behaving according to what we believe. If we do a back surface configuration, and I'm using ALUMINA, aluminium oxide here, to show the rise time. And the rise time here we see is around 30 nanoseconds. I've chosen ALUMINA because ALUMINA has a very, very fast rise time in the system. So that is an important factor. Pick something with a fast rise time, generally a ceramic. If we want to look in a little bit more depth about how manganin behaves itself, then we have manganin, its stress versus change in resistance here, showing it does not have a super large change in resistance with pressure. But if we look at its composition, then it's an alloy made of copper, magnesium, and nickel. That's why it's manganin. And it's commercially cheap, which is good. Its change of temperature, change of resistance with temperature is very small, approximately zero. It's not absolutely zero, but it's close enough for the kind of changes we're going to see in the stress range of operation. And it changes its resistance by about 0.25% per gigapascal. These are numbers you can look up in the literature very easily. It's well calibrated, both as a wire and a foil. And its operating range is generally between 0 and 40 gigapascals. The thing that limits its usage is the breakdown of the polymer. The polymers become conducting at these higher stresses. And you can buy them in a number of shapes and sizes, and generally you aim for a gauge resistance of 50 ohms. Why 50 ohms? Because a lot of electrical devices have electrical impedances and termination impedances of the order of 50 ohms. It's a fairly standard industrial device setting, so 50 ohms is a good value. Okay, these are just some pictures of what these gauges look like with some idea of the dimensions. They look like any other form of a gauge, in the sense of there are some thick legs down which the power is delivered. There is a sensitive region consisting of thinner wires. So nothing particularly unusual there. At the bottom, we have an example of a lateral gauge. Now, please remember that with the two gauges at the top, the stress is going through the screen, through the face of the screen that you're looking at. Therefore, it's compressing across the whole area of that gauge, more or less simultaneously. For the T gauge at the bottom, because it's inserted laterally, the stress pulse is going to sweep across, so it's going to go along the screen. And this means that the active width, the area that is doing the sensing, is around about 240 microns in width. meaning there's not such a great time resolution. You can look up the change in resistance with stress for manganene, and there's a curve. People keep adding points from time to time in the literature. Absolutely no problem there. There is one thing with manganene gauges, as with all gauges, check for hysteresis. Hysteresis in this sense meaning that you get deformation of the gauge above about 1.5 gigapascals, called a work-hardened gauge. It's a kind of plastic limit with the manganene. You've got this residual strain, and that leads to a residual resistance change. You've changed the dimension of the gauge. The length over area has changed. Therefore, you have this wonderful residual resistance, which can be around about 10%. So, has hysteresis in manganene gauges been calibrated? Yes, it has. It can be looked up, and your readings can be corrected for release. So if you keep shocking the gauge up and up, you can fairly directly measure the stress, but coming down on release, make sure you know if hysteresis has occurred in the gauge, and that occurs if the measurement in the gauge is above 1.5 gigapascals. Okay. Now, manganene is well characterized. It's got a fast response. Its hysteresis is above 1.5 GPa, so let's be careful there. Can be used to measure several components of stress. Again, you notice with care. I keep saying with care because do not ever fall into the system of just putting a gauge there and crossing your fingers and hoping that it's going to work. You have to really think about it, and if you've got the capability, model what you expect to see beforehand, then compare it to the experiment. You can buy shapes and sizes, it's all good, and you need a power supply. Okay, so that is a little summary of an example of a piezo-resistive gauge. Let's have a look at the piezoelectric one. So PZT, lots of different kind of ceramic, kind of fairly brittle gauges there. PVDF is a polymer film. It is stretched and taken above its glass transition temperature. You've put a huge potential across a kind of 5,000 volts across a 240 micron thick membrane or a 50 micron thick membrane, and let it cool whilst having that high voltage applied to it. That will freeze the direction of the polarized components in the polymer into a certain orientation. That's biaxial stress and small char and pole. When you compress the crystal, you get charge out, and therefore what you're doing is measuring charge when the strain of the gauge changes and the strain of the gauge changes when you change the stress. So pretty useful, and you can use it as films or you can use it as blocks. It's all fine in that respect. And if you're going to use quartz, it ultimately will shatter, so less than 5 GPa. Quartz is well calibrated, but it's non-linear, so you have to be careful about there. So let's have a look at what a PVDF signal looks like compared to a manganene signal. Now, PVDF, because it gives out charge, you integrate the charge on something like a resistor and something like a capacitor. Apologies there. You integrate the charge on the capacitor, you capture the charge on the capacitor, and from the charge you capture, you work that back into a charge given out by the PVDF. From the charge given out by the PVDF, you know the strain in the PVDF, therefore you know the stress in the PVDF. That might seem like a lot of steps, but there are graphs out there that will help you do that very quickly. So here is an example of an impact upon a copper target that was 5 millimeters thick. We had a PVDF gauge, then 5 more millimeters of copper, then a manganene gauge, and then 10 centimeters of copper on the back. And we struck that with an impactor going around about 500 meters a second. That was a copper impactor. And here we see the pressure measured in the gauge, or stress in the gauge to be more correct. Stress in the gauge in the PVDF, it went from 0 up to around about 6 gigapascals fairly quickly. The manganene gauge, it's an embedded gauge. The rise time is 200 microns. you'll see a rise at 2 microseconds from 0 up to around about 6 gigapascals, 6 millibars. It's very similar, not a problem there. What you will see is because PVDF releases charge, and because stress gauges such as MANGANIN have an antenna they have a kind of electrical receiver like shape to them. They've got these coils of metal there. You will get electrical pickup between the PVDF and MANGANIN. This can be useful for time of arrival if you're so interested in such things. However, it also means you cannot use PVDF and MANGANIN if the stress will arrive at those gauges at about the same time, because the electrical disturbance from the PVDF gauge will affect your MANGANIN reading. So, first instance, be careful with what types of gauge you put into your system and where you put those gauges. Here's a calibration curve for PVDF, charge given out per unit area of PVDF linked to stress. So these kind of curves are very useful. PVDF is not as widely calibrated as MANGANIN, so people keep adding to the accuracy of this system. Now, those are a couple of examples, but let's have a look at some of things that we've got to take a lot of care with. Sample impactor alignment, multiple waves, time to equilibrium, and gauge insulation failure. This is a thing and a lot of colleagues of mine talk about. Plan your experiments, model them first if you can. If you can't model them, then at least get a piece of graph paper and draw distance time diagrams to work out what you expect to see first, then plan your experiment. So here is an example of what happens with gauge and impactor target misalignment. It was a deliberate misalignment here. I had a well-aligned impact experiment, and that is represented by the red line. The red line on the graph there has a very sharp rise. And then I deliberately misaligned the target by 1 degree. That is a lot of misalignment. It's the kind of thing you can obviously see looking by eye. So 1 degree misaligned gauge, really quite extreme. And down below, we have 3 frames from a high-speed sequence. In this sequence, this vertical line is where the gauge was, and this angled line represents the shock wave coming through the perspex. So the shock wave comes through the perspex. The gauge is about here. That line, that angled shock wave goes through. The shock wave runs across the gauge. Doesn't hit it all simultaneously. Runs across the gauge, and then that shock wave is gone. And what this does is it ramps the rise of the gauge, which is not unsurprising, but very importantly, it's that angled impact, that angled wave has compressed the gauge as well as putting it under stress. It's shrunken the length of the gauge. It's made it smaller. So that's changed the resistance. That geometrical change has changed the resistance as well as the stress. So what we see here is the output is ramped, but also it's to a lower stress level that you think you record. So what this means is you get an inaccurate measurement, and you can see that's quite a substantial amount of change. So angle of your the stress gauge, seeing an angled shock wave is not so great. Now, let's say instead of perspex, let's put that gauge within copper and let us deliberately misalign by, again, 1 degree. And what we see here in the copper is that because copper has a different mechanical property to the gauge, copper compared to perspex versus gauge, the effect of the angled line is, yes, that angled impact does take a longer rise time, but now the combination of stress and strain produces a higher reading in the angled gauge. So this combination of stress and strain states and alignment can give either lower or higher stress levels compared to well-aligned targets. So what we're saying here is, if there's misalignment, you cannot really trust the measurements you are getting. How can you measure misalignment? Time of arrival pins, high-speed photography. There's a number of ways of doing it, but alignment is important in plate impact. Then let's have a look at sample roughness. Now, sample roughness in Hopkinson bar experiments is not such a big effect, because in Hopkinson bar experiments, we're looking at bulk failure, bulk flow of the sample. There are waves in the system, but it's not particularly a wave-dominated response. Here in this system, in shock waves, we've got a wave-dominated response. So therefore, surface roughness and things that affect the initial transmission of waves is important. So 3 experiments here with different amounts of roughness on the sample. So in the first case, we've got a face plate. It's a couple of millimeters thick, and we make it smooth. Then we make it rough by putting grooves in it, and then we make it very rough. Now, if you think about this a little bit, what we are saying is we've kind of made the surface of the front of the impactor very much like a granular material, and we will return to granular materials later in this lecture series. However, what we're seeing here is the effective roughness of the impact face on the gauge. So there is the geometry. We've got an impactor coming in there. We've got some velocity pins. We've got our grooved copper plate. We've got a copper plate. We've got a perspex backing plate. A couple of gauges in the system, MANGANIN gauges, should be fairly straightforward. And here we have just the raw output of smooth versus rough at low impact velocities. And what we see here is the gauge at the front. We can see there is ramping in the gauge. Not an issue. Again, you can say that's due to this time it takes to collapse down that roughness on the surface. That's what's happening. On the front and on the back, you can see that the roughness is affecting the rise time, but the ultimate stress you record is very much preserved. Good. That is the ramping due to the grooves. Your shockwave comes in. It takes time to flatten out and cause flow within those grooves to basically produce, through impact, a smooth surface. Now, the width of the ramping zone can be relatively easily estimated through considering how long does it take a shockwave to reflect as it goes through that rough surface. And you can compare rough versus very rough and see where the ramp stops in the gauge traces. And in terms of time, you can do a fairly reasonable estimate. At 900 meters a second, the impact velocity is so fast that the roughness on the front of those perspex gauges is flattened very rapidly, and it goes to a time below that of the time resolution of the gauge. So it's below the time resolution of the gauge. So what we see is basically no difference between smooth versus rough gauges. So time response of the gauge and time response of the phenomena you're trying to measure is an important factor. And that difference between the phenomena you're measuring and the stress you're applying will change as you go over stress range. Sometimes it will be a slow process and you will easily see it. As you hit it harder, it will become a quicker process, a more rapid process, and you may not see it anymore. So please bear that in mind when you're using diagnostics. And here's an example of that perspex target at 250 meters a second, putting those traces together. Front gauge, rear gauge, everything looks nice. let's have a look at a very rough target at 250 meters a second. So this has got really big grooves on it. And what you see are extra features due to initial stress transmission through the rough target. And you get this peak. And the surface roughness, again, isn't affecting the final stress. Look, 0.39, 0.37, 0.39, 0.36, you know, very good agreement. But the detail we're seeing here is much different. You've got this extra peak caused by initial stress transmission through those rough peaks on the front of the gauge. And then those that perspex, that polymer kind of collapses and the stress collapses as it starts to flow. If you didn't know what's happening, you may think there are extra phenomena occurring in this impact. And that can be quite worrisome because you could attribute this to some new physics, to some wonderful new phenomena that's occurring, and actually it's just the roughness of the gauge. So, you know, roughness of the target. So please bear that in mind. Right. Foil strain gauges, one of my you know, least not so commonly used in shock waves, but very often used in dynamic experiments. You know, you can just have semiconductor gauges, you can look at bending in optical fibers. These are all techniques that have become very well established. You can have foil gauges, which I've used quite extensively. And again, electrical gauges here, they change their resistance with length, and you can buy them at a range of initial resistances and match them to your experiment. And again, they have a standard gauge like electrical gauge like construction to them, thick power lead legs, and you've got a measurement direction along the length of the gauge. And very simple relationship that you've probably come across very early in your lives in school, when you got to kind of in the UK, when you got to be 14, 15 years old. Resistance equals resistivity, powers by length divided by area. And the length is the length in the thin regions, and the area is kept thick in the power leads to reduce the effective area on the system. And the gauge factor, change in resistance with change in stress, and therefore strain. G generally has a value of around about 2 for most metals. And basically, you know, the resistance changes with changes in length as the area, change in area is small. So that's all okay. We can put those gauges into use. And I've done a series of ballistic style experiments, reverse ballistic style experiments, where I've put a gauge on a rod and fired a rolled homogeneous armor, so a strong steel plate at that rod, and basically measured the strain in the system using both upper and lower strain gauges. And here is the variation of strain with the angle there. Now, the details of this is not so important. The main thing is, though, on this one, the upper gauge, 9 degrees, the one at the top, the one with the circles, dips down very quickly. -6 degrees, stays flat for a very long time. So that's on the upper gauge. On the lower gauge, 9 degrees, stays flat for a very long time, then goes down, and then -6 degrees goes down quite quickly. So what you can see here, from there to there, there's almost a complete reversal in the behavior of the gauges with this angle. So what we're showing here is that if you change the angle, you will have sliding followed by penetration through the plate, and the bending moment on the rod will act to bend it away from the target. And if you have the angle more normal to the rod by a few degrees, then you can get the bending of the moment, the bending of the rod into the target, and a kind of more cutting before penetration occurs. The other thing here that is of note is that in most cases you've got a monotonic style shape to the gauge trace, but you'll also see on the 0 degree curve here that there is a peak. On these ones, you'll see this peak more clearly. So this is showing that there is some flexing of the rod during impact. So the rod bends and then kind of recovers back to a linear rod without any bend in it before the full penetration occurs. So there's some flexing on the rod as well that you are detecting. Okay. So strain gauge is not so commonly used in shock experiments. That's why I've only got one example of it here. The final kind of gauge I'll talk about before briefly mentioning velocimetry is a particle velocity gauge. These are very, I'm going to say old-fashioned, but these were amongst the first type of gauges to be used in shockwave studies. And they're used in non-metals because you have to get a magnetic field touching going through a wire, and you measure a voltage, and it's using electromagnetic induction. So the key equation there is velocity equals magnetic field strength times length of gauge times velocity. So this is a very simple equation of electromagnetic induction. We like that kind of simplicity. And you can put your fine wire or your foil embedded within the gauge, and you get a steady steady field perpendicular to the wire, generally produced by a solenoid, and you impact it and you move the wire with the shock wave. The wire moves with the material. You measure the particle velocity of the wire, therefore you measure the particle velocity of the material. It's an gauge. There you go, you measure the induced EMF. So you can put a couple of Helmholtz coils, a couple of wound coils at a distance and measure the field strength between them. I will point out that you need to ensure that the current is going in the correct direction in both coils. If you get it the wrong way around, you can have one coil cancelling the other out, which means you don't get any field where your gauge is, and life becomes difficult because you don't get a reading. So you can measure that, and we set up some gauges with a couple of coils, produce the magnetic field, measure the magnetic field down below. As you can see, it varies quite strongly. Your second version involves putting a fixed magnet, steel, and what you've got up there is an example of it, a coil with a fixed magnet. The coils act to reinforce the magnetic field of the fixed magnet. So again, careful about current flow direction. I put some dimensions on them. It's not so deeply important, but that is the diagram up above, and below is an example of what we put into the end of the gas gun, where you can see some wood and some strapping and a couple of coils there. The coils survived multiple experiments before being destroyed, which was good. And you've got a reasonably good uniform magnetic field there. You can see I'm getting 200 Gauss in the system. Before I was only getting kind of 20. So spending a little bit of effort getting a fixed magnet into the system made a very large difference. And that's the experimental setup. You cannot mount your sample on a metal ring. You've got to try and keep metal away from the whole thing. So we had a polycarbonate plate, we had some metal studding, and we had a gauge very much as shown there, with multiple wires of slightly different lengths leading off to the oscilloscope. And these are the type of responses we got. We changed the thickness of the wire and repeated the same experiment. What you find is you've got thick wires, went to the 200 meters or so impact velocity very quickly. Thinner wires got there a little bit quicker. Too thin a wire had a lot of noise, and that was because that wire was being very badly abused by the material it was mounted in. So what wires can you use in particle velocity gauges? Well, too thin, damages too quickly. Too thick, the inertia of the wire slows the wire relative to the material. You can look in the literature. There are some guidance given there, on wire diameter. P is the required response time. So a couple of very simple equations there based upon a fluid motion, and you can estimate the response time of gauge that you're after based upon the D, the wire diameter, the required time, the particle velocity, and A, which is this term, and we were using copper wires, so the term on the top there is density of copper. Density 1 down below is the density of the material that we're trying to measure. So you've got this very rough guide there. Is it, again, as I keep pointing out in these lectures, can you find a more involved full derivation? Yes, you can, but here are some guidelines that can help you decide on what you're going to use in the laboratory. Now, a couple of things before to finish. Measurement of shear stress. Shear stress is an indication of a material's ballistic performance. If you read older literature, then if you read particularly shockwave literature, you will find people trying to do what they call predict the cold compression curve using various forms of quantum mechanics of various theories, which is fine. And the offset from the cold compression curve and the shock Hugonio is 4/3 of tau, where tau is the shear strength of the material. So a combination of theory and experiment, but where one curve is very theoretical and the other curve is very much measured by experiment, the combination of those two can often be very unhappy because they come from two widely different set of assumptions. Obviously, in experiment, you're saying the experiment works because the gauges tell me the truth. And in the calculation, you tell me that the calculation tells you the truth because it's based on very solid theory. Both of those positions are hopefully correct. If everything works, the measurement is accurate. If things don't work, then people say, oh, we need more experiments, more calculation, etc. But if we can measure both experimentally, at least we've got a reasonable footing for comparison. Okay, not the absolute truth, but a footing for comparison. So this is where one of the reasons I first ever spoke to Oleg, and this is many years ago, and it was failure waves, so a failure phenomena seen in glass, and first noted because we measured the longitudinal stress in some window glass that we impacted at 5 gigapascals, and the red line shows the longitudinal stress using a MANGANIN gauge, and it's very straightforward. You got a rise time, gets to a flat top, nothing there that would make you think anything was happening. Single shock rise, nice final stress, nice kind of fairly boring really response. It goes up and it stays there, it's nice and flat, fantastic. However, when we measured the transverse stress, we could see that there was a step in the system. So using the lateral gauges that I mentioned at the beginning, you got an initial rise followed by a second step up to a higher level. Now, shear stress is the difference between longitudinal stress and transverse stress divided by 2. There's a convention there, but it's the difference between those two things. So what we see here is initially the difference between those two amounts to a value of round about 3 gigapascals. So that's a measure of the shear strength of the system, or the shear stress in the system. What we then see as we go later on, say to 1.2 microseconds, that difference has now dropped to more like 1.25, maybe 1 gigapascal. So what we're saying is the shear stress, and by implication the shear strength of the material, has dropped. It's become more like a hydrodynamic, a kind of all stress components are equal situation. So the strength has drained away from the material during that impact process. Now the next slide shows high-speed photography of an impact of this type. So it's a movie. Top of the face here is the impact face. At the bottom of it, there's a perspex glued onto the back where a gauge was mounted. And here we have a bulk of the glass. The impact happens here, and the wave is going to move down the screen. So let's play this a couple of times. So impact happens, and we get this thick black wave. This is a shock wave moving down to that interface, and there you go, impedance mismatch. Some of that wave is transmitted and some of that wave is reflected. Great. But now I'll point out the other really obvious thing is this black front behind. In a region of shock compression, the glass becomes opaque. Not here, but after a period of time. And this is due to the nucleation and growth of micro cracks and their interaction between one another. So this is where Oleg and his group have looked at these kind of phenomena where you get a number of kind of radiators interacting with one another in a bulk process where the population includes nucleation and growth of these multiple micro cracks affecting the material property. Basically, the glass turns into a powder, and a powder that has a permanent densification associated with it. So an interesting, and if you're doing armor ballistics, important process. So that was glass. The next question comes, what about ceramics? So people get very excited and they say, okay, can we introduce this failure wave phenomena, which was first seen in Russia, incidentally. It was seen in the mid-1970s. So it is a Russian discovery. People in the West have rediscovered it since, like we did in the mid-1990s. But there you go, it's done in Russia, and excellent, well done. And what we had there was, in this case, a couple of targets. We have one target where we just had the lateral gauge mounted and we hit it with an impactor. And the other one, we had a lateral gauge mounted and we put a cover plate on the ceramic and we hit it with an impactor. What we discovered was, if we did that scenario for glass target with or without a cover plate, we got the same result. There was a failure wave. But for ceramics, which are hard and brittle and high strength compared to glasses, we got quite different results. So for alumina, with and without a cover plate. So the one without the cover plate is the blue line. You can see there is a rise followed by a plateau, followed by a second step. So it looks like the glass. There is a decrease in the shear strength of the material. The red line, where the cover plate was present, does not show that effect. Okay. You then change the impactor. You say, forget about cover plates. Let's just hit it with a copper impactor, or let's just hit it with a tungsten impactor. And what we see here is that there is, if you use a copper situation, a copper plate, measuring the lateral stresses at two distances from the interface, you see for the copper, the 2 millimeters, you're going to a much higher lateral stress. If you go deeper into the target, 6 millimeters, it's always a much lower stress with a longer ramp time. With the tungsten, with the harder impactor, trying to induce the same stress levels in the target, hitting it at a different velocity, what you see is that at 2 millimeters, you're just getting that lower stress level. So cover plates have an effect, and the type of impactor has an effect. What is happening? Well, actually what is happening is that you're getting jetting of material into the gauge location. So this is a gauge. It's got a cover plate on it. This shows it here, or an impactor hitting it. And what we see here is the impact interface, and we're getting motion of impactor material into that interface, and that is causing fracture within the sample. So that stress concentration here, that pushing of material into that lateral cut, is producing that failure wave-like effect. What we're saying here is the geometry of the impactor, geometry of a target, has a big effect for ceramics. You can induce a thing that looks like a failure wave, but it's not a failure wave like you see in glass. It's a failure due to extra cracking introduced by the presence of material jetting into the cut. So take care when fielding these types of gauges. Take care with the geometry. Use high-speed photography. Use whatever diagnostics you have to look at if that gauge is having a strong effect upon the material behavior. Otherwise, you could start drawing some really quite interesting, and is the word crazy, you could start making some very bold claims based on a flawed experiment. So again, be careful. Final little finish off, a quick look at velocity interferometry. Very important technique, very popular at this point in time. You can look at the VISAR, which is a velocity interferometer system for any reflector. VISAR, developed by Lynn Barker and colleagues in Hollenbach in the 60s and 70s. They were looking at the motion of clouds in the sky. Very nice. However, this gentleman works for Los Alamos, which is a nuclear weapons laboratory, and they were measuring the velocity of radioactive clouds moving across the sky from nuclear weapons tests. It doesn't sound so attractive when I say it like that. It's a kind of microsonic interferometer, and what you're doing is you're using a Doppler effect from reflecting a laser from a surface, and by measuring the effect of the Doppler shift, you can basically get a measure of the velocity. And what they do is you reflect the beam off the surface, and you delay one beam in time by sending it through a optically dense material, such as a block of glass, and you let the other beam travel mainly through air. There will be a time difference because obviously refractive index is a measure of how much light speed is reduced, and therefore you can introduce this time difference between the two parts of the beam. When you recombine them, if there is any frequency difference, you will get a beat frequency. And that beat frequency, that fringe count, is proportional to the velocity change. So that's what a VISAR looks like. You've got light coming from the sample, so it's taken into a beam splitter. The blue line, the lighter blue line, goes through the beam splitter, through the etalon, reflected off a mirror, comes back through, and the etalon again comes back through the beam splitter, and off it goes to the left. The other one comes in, gets reflected off the beam splitter, goes to a mirror, goes through the etalon once. So one lot of light being through the etalon twice and reflected once. The other light has been reflected twice at the beam splitter and at the mirror, and through the etalon once. The etalon changes the time, but we've got to be careful here. We know that reflection of light from surfaces causes a phase change. So that is the reason for the 8th wave plate introduced in front of M2, just to account for that extra reflection that is seen by one of those beams of light. This is the kind of data you get out of it. I mean, I wouldn't expect anybody to interpret this data as it stands, but it's an example of the kind of output you see from a VISAR, showing intensity of light, dips and changes in intensity of light. And when you analyze it, you get the particle velocity versus time. There are a number of programs people use to do this analysis. Lynn Barker and colleagues produced a company called ValLin, and their analysis software is as good and as well accepted as anybody's, and we tend to use it. So you can get particle velocity versus time. Very good. What we can then do is using manganin gauges and VISAR gauges simultaneously in the same experiment. Manganin is measuring stress, VISAR is measuring particle velocity. We get those lines, and they're quite similar. So there is a system called heterodyne velocimetry, also known as photonic Doppler velocimetry, a new technique. It's becoming very well established. Analysis algorithms are not so clear. Nobody's really decided on, this is the absolute analysis program. There are a number of analysis programs that give very similar results. Uses Doppler shift of a system. And the idea here is you could have a moving target and a thing called a circulator, and there's a Doppler shift at the moving target. You then send that shifted light, combine it with light from the laser, send it to a detector, and measure a velocity versus time. And this is very good. You can field it in different formats called phase shifted systems, or you can use two lasers to allow comparison between the frequency of the light from those two lasers, and different configurations exist. They're still being developed, but the main thing is it's lower power in terms of the lasers used, and also you tend to have clearer results at the moment using heterodyne velocimetry in terms of the velocity you reach. You can use them in plate impact experiments and get a number of results from them. So this just shows a series of results gained from a single experiment where we use probe 4 to measure the impact velocity, and the other probes to measure the response of different samples mounted on the target. So in conclusion, hopefully this has been a little bit of a revision for showing that optical gauges and gauges of various types can be used. Velocimetry is increasingly common. Please be aware that in any type of experiment, there are technical limitations on time. There are interference effects caused by the sample and also by the environment in which the gauge is placed. Wave angles and reflections are important, and there can be optical effects if you're using velocimeters caused by changes in the refractive index of the materials you're looking through. So all of these are kind of single point, or if you tell me a gauge occupies a small area, I'll say a single point or small area measurement. It's good for looking at those locations. What's happening in 2D and 3D is going to be the subject of my talk tomorrow. But I hope in this you've got an idea about what can be done looking at single point measurements. I think that's that. I shall do that. I shall come back on here. I shall stop sharing my screen. There you go. So hopefully now today I've got a lot longer to talk. I have no lesson for the next half hour. So if people want to talk, I'm happy to talk. If people have to go, I know they have to go.
Debbie, thank you very much for your marvelous talk, and this talk excited in me the remembering and recognize time at the Cavendish Lab.
Okay, thank you.
Thank you very much. And colleagues, please questions. We have unique opportunity now for questions. Please, our experimentalist Sergey, and not only experimentalist.
Great. So the one thing I will say is it's now, if people have been reading the literature and keeping up to date, which I hope they have, then a lot of this presentation will say, we know this already. And what I always say to my students is, if you go to a talk and you know all the material already, that's really good. It means you're up to date. It means you've learned things which are quite important. Fine. If you go to a lecture of this type and you discover 2 or 3 things you hadn't heard of before, good, you've learned something new. That is useful. And then my final comment is, if somebody comes to a lecture like this and they really didn't understand anything, they really need to be in the lecture. So none of this time is kind of wasted, but I hope people think about this a little bit. I'm very happy to answer any questions on a longer time basis. This is a collaboration. Hopefully it's going to keep on going for a fairly long period of time. So please don't be shy. I don't mind questions of basically any nature. If I know the answer, you'll get the answer. If I don't know the answer, I'll tell you I don't know. But the main thing is, please ask me some questions and I'll try and give you an intelligent answer to those questions. Send me an email, please. Please be welcome. My email address is down there. I'm due to talk tomorrow. Is that a correct statement as well?
Okay, Bill, let me please. Do we have a few minutes just to discuss? Bill. Bill.
Yes, certainly. Yeah.
Yes. May I ask you?
Oh, yeah.
What about your opinion? Because you were talking about several methods to record shockwave profiles, and it's still unresolved. Fundamentally, question concerning the nature of elastic precursor decay, according to my feeling. Yes.
Yeah.
Because it's really the deep roots of transition from to elastic, from elastic to plastic behavior. And what about your feeling? The elastic precursor decay nature that traditionally, not traditionally, but historically could be considered from both point of view, from thermodynamic point of view, yes,
yeah,
and from analytical point of view as relaxation. Does comparison of transition from elastic to plastic front due to the elastic precursor decay and scenario of failure wave generation, because it's also the consequence of the collective behavior of microshears, yes, due to the formation of failure wave front. There is not some similarity which could allow us clarify the nature of elastic precursor decay, its thermodynamic nature or relaxation nature, because it's a permanent question for me.
Yeah, so I think the phenomena of elastic precursor decay, which has been looked at particularly with respect to materials like ceramics, for example, and that's where I've mainly seen reference to it, is a lot of the time it's associated very much with phenomena occurring near the impact phase. And then as you go through the material, the wave kind of changes. And for me, it's because it originates, or something originating at that impact phase, which is quite important. We have these region of space where you have a big difference, generally a big difference in density of the impactor and the target, or there's some small geometrical shaping of the impactor and the target. You get the impact there, and you measure what is generally a very high elastic strength in the material at that phase. As you go further in, that elastic stress tends to die away. Ultimately, it kind of asymptotes. If you get sufficiently thick material, it asymptotes. And so in this initial region, it's like the system, I would argue, you call it relaxation. I would argue in a very similar way, I just use slightly different words, that the system has not matured enough. The system is still undergoing all of those effects of inertia. The failure processes still haven't had time to set themselves in motion. And so the material is relatively in initial stages, it's taken to high pressure, but once cracks start to develop, once cracks start to nucleate, those transmit information into the material. That takes time. So initially the material's hit, it's relatively unmolested, undisturbed material. It goes to those high levels. Damage starts to grow with time, and that's what causes the decay. Now, if I'm a ceramicist, as a person who works with ceramics, I will talk about micro cracks micro shears, those kind of things, because I'm very used to material failing in a ceramic mode in that way. If I'm a metallurgist and I work mainly with metals, I will start talking about dislocation formation. I'll start talking about work hardening. I'll use all of the terminology that I use from a metals background. And what I will be saying is some things are happening at the surface of the metal. They take time to occur, takes time to grow, nucleate and grow dislocations. It takes a little bit of time to get some of those types of dislocation to move quickly along different crystallographic axes. It will take time for equilibrium to be reached in terms of the flow process, and they will die down. So with failure waves, it's almost like it's elastic decay in terms of the phenomena. You see, it's like elastic decay, but bigger scale. You're dealing with things that take microseconds now, not sub-microseconds like a lot of the precursor decay phenomena. But things are occurring over long microseconds, and you see that more. You see that step. You can use a similar type of explanation to look at elastic precursor decay. The main thing that limits us is the accuracy of the experimental methods, particularly at interfaces where there are reasonably large differences in impedance of the material, because we get different types of flow instabilities of those interfaces. But it's those flow instabilities that help initiate those kinds of micro shear processes, I believe. So that would be my take on the link between my interpretation between elastic precursor decay and failure wave. I do think they show different relaxation processes, and I would suggest that they would probably be quite similar processes. Why? Because the material, a given material, only has a certain number of ways it can modify itself during the impact process. So yeah, that's so. I hope that's a reasonably clear explanation. Oleg's a far better mathematician than I am, so he can no doubt show what levels of population of defects are required, what relaxation times are required to produce a given profile. But the fundamental processes behind that profile are due to activation of damage processes followed by their growth and interaction. So yeah.
Bill, thank you very much. May I emphasize the reason of these my questions? Because the main goal in the framework of project that we are, it's to establish both experimentally and theoretically similarity in the behavior of solid and liquid in shocked liquid, yes, in the links with the so-called gate momentum states, when liquid reveals the elasticity in the gap in the wave number space. In the gap, yeah. And just today it was the first lecture by Matteo, and I would like to ask my colleague to send you his presentation today, because I think it will be extremely interesting after the cycle of your lecture and lecture by Matteo to establish seminar with our key presentation concerning experiments and interpretation of results in shocked liquid. Yes.
Yeah.
I think combine our abilities in the experimental techniques and theoretical ability. And I would like to attract your attention, Bill, that the question, liquid, according to our feeling, could reveal the momentum transfer according to plasticity mechanism.
It doesn't strike me as at all unusual. I think it's a phenomenon that definitely needs to be investigated, because we do know that as we go to those higher strain rates, and also we know that at the higher strain rates, processes have less time to occur, and people have a view of a liquid as these semi-randomly arranged material with weak bonds between them, either being, hydrogen bonds for water, dielectric style bonds for other liquids, and then we impact them, and depending on the structure of the molecule, but also depending on the strength of those interactions and the time scale, so like the viscosity, then we affect how the compression of those things, and therefore how the energy transfers between the liquid molecules and the strength of the bond between them. They don't have time to move, so they're almost like frozen into a structure. And it would not surprise me if there were momentum modes which were more specifically accessed.
Yes, Bill, I totally agree with you. But the question is, what is the characteristic time? Yes.
Oh, yeah. Yeah, absolutely. Yes. I would. What is the characteristic time? I would say the characteristic distance, and we could look at things like any kind of precursor decay within liquids. That would be my first estimate. The other thing we've got with liquids that we can do quite well, particularly with water, is do experiments at different base temperatures, so we can affect the bonding between those molecules, how much we free them to move. So I'm going. If you said give me a time scale, I'm going to say less than a microsecond, because I've done the impact upon liquid.
I think it's close. I think it's close, microsecond.
Yeah, that would be my initial guess, but I think we could do some more focused experiments, because I'm generally hitting liquids to cause a reaction, or I'm hitting a liquid to cause some kind of spallation or cavitation within the liquid, and I see those cavitation processes occurring on the kind of microsecond time scale. So I can see the bubbles nucleate.
Okay. Okay, it's extremely interesting, your proposal, and more. I would like to say more that is according to the rules of this project, we need for the second year project to discuss and to have to use the opportunity to send maybe PhD students at the institute that maybe we could prepare joint experiments.
I have a colleague who does pulsed power experiments, and we've been exploding wires within liquids.
Okay. Similar to our, we have also this experiment.
Yeah, and we've been using multiple wire arrays to produce converging shock waves. Okay. For people who like converging shock waves. So those are the type of experiments that we could work together on, and certainly use your diagnostics, our diagnostics, and the theoretical.
Where is it? It's at Imperial College or another place?
No, at Imperial College in the basement. We have a thing called MAC and Magpie, and they're both for doing pulsed plasma or exploding wire experiments. But these are plasma physicists. That's what the equipment.
Okay.
But being used to look at these kind of coupling between exploding wire and the shocks moving through liquids of different types. So this will be a very good area. And we've got an isentropic compression experiment, which we call MAC, which we're using mainly on polymers. But liquids will be very easy to introduce into that system.
Okay, yes, it's very exciting opportunities. And may I ask my colleagues, please questions if you are ready. Okay, I think they're excited.
It's all right. I mean, I when I was a younger, earlier career person, I used to go to these lectures, and they used to bring people in from various parts of the world, and I used to sit there very quiet, and I used to think, and sometimes I thought about other things, but sometimes I thought about the material they were talking about, and it takes a little bit of time to, particularly if they're giving a lot of information, to assimilate what's being said, and also, how does what's being said relate to the experiments that people are doing? So I don't expect lots of questions, but I hope people come up with some questions, and feel free to send me to them. I'll speak to you tomorrow morning about 2D and 3D, and we'll kind of take it from there. So thank you, Oleg, and thank you, attendees, and thank you to Irina. And I look forward to speaking to you tomorrow morning, and later.
Yes, Bill, cordially thanks for
Very welcome.
your nice job. Thank you very much.
Thank you. Bye-bye.
Bye.
Thank you. Goodbye.
Bye-bye.